All right, hello everyone, and welcome to Talk 11 of the African Plant Breeders Association and African Bioinformatics Agri-Informatics Lecture Series. Today, we're lucky enough to be having Dr. Vamsi, who will be taking us through machine learning foundations for genomic prediction. Dr. Vamsi holds a PhD in statistics from the University of Nebraska-Lincoln, where his research focused on improving genomic prediction using high-dimensional modeling and multi-type data integration methods. Dr. Vamsi's research interests include machine learning, dimensionality reduction, and genotype by environmental interactions in genomic selection. Currently, Dr. Vamsi is a senior research data scientist at Roblox Corporation, where he develops statistical methods for large-scale online experimentation with a focus on machine learning. And he'll be taking us through machine learning foundations for genomic predictions today. So thank you, Vamsi. Over to you.
Thank you so much, Samir. Hello, everyone. Morning, afternoon, evening, wherever you are. I'm on the California coast here in the US, so it's about 7 a.m., so I will say good morning. Uh, so today we'll go through some of the foundations of machine learning and how it can be applied to genomic selection. We have another talk later this week where I'll focus a little more on applications of some of the methods that we see. So you can think of this talk as kind of those little foundation building blocks. How do you think about machine learning in the context of genomic selection? But even generally, like what are the principles of machine learning modeling? And and then in Thursday's talk, we'll look at a few applications, successful applications of machine learning, and then also a quick intro towards artificial intelligence because it is all over the place right now. How can we, as researchers, geneticists, plant breeders, access AI to help us research better and work on our stuff better? But as I go through these slides, please feel free to stop me anytime you have questions, put them down in chat, or just raise your hand so I'm able to pause and take your questions. Does that sound all right? Just maybe just want to see people maybe thumbs up or anything. Yeah. Awesome. So with that, let's jump into the material. The goal kind of today is to learn how these models work. How do you evaluate them correctly? How do you decide what's the best model for your data? How do you choose between a complex model and a simpler option that actually helps your plant breeding decision? One thing, a couple of notes in terms of terminology as I go through this entire talk. So I say machine learning foundations for genomic selection. I will use the words genomic selection and genomic prediction kind of interchangeably. Since most of today's talk focuses on the statistical methods or machine learning methods, we're focusing on genomic prediction really, not the framework after for the selection, but I'll use these words interchangeably. And then the other thing, of course, most of you will be familiar, but just in case, for machine learning, I will keep using the shorter form ML. Yeah. Okay, so let's look at what we'll look at today. So first thing is like why do we even want to do machine learning for genomic selection? What are the benefits that machine learning can offer that some of the other statistical methods, traditional statistical methods may not be able to offer? And then we'll go through the basic blocks of an ML workflow. I would say like this is one of the uh, key takeaways from this talk is how do you think about an ML workflow? And then the other part is I've structured the talk very intentionally as focusing on evaluating the ML models before actually introducing the models itself, because I actually think it's way more like it's very important to know what you're evaluating and you determine before you choose your models how you will evaluate those models. And that allows this kind of independence between your evaluation strategy and your model choice, and it generally leads to better ML workflows. So within the ML methods itself, again, today is not like a comprehensive deep dive into every single machine learning method that exists, or even going deep into any of these methods. But in general, we'll talk about regularization as kind of a stepping stone between linear models and machine learning methods. And then we'll spend a little bit of time on trees, random forests, and ensembles. So random forests and ensembles being these larger structures on top of a building block called tree. And then finally, we'll end with neural networks, which can be intensely useful, but also notoriously difficult to implement, especially in genomic contexts. And then I will kind of try and put together the different things that we looked at today towards the end. I see some chat popping up, so let me quickly have a look. Okay, it's just Sumer's message. Okay, perfect. So why do we want machine learning for genomic selection? Machine learning has several applications throughout our day-to-day life. You see machine learning used significantly on your phones, on your internet, and also in genomic selection. So one thing with genomic selection or genomic prediction, traditional genomic selection, uh, models began with like this additive and linear view of genetic effects. Essentially, like every marker that you have in your genomic information contributes an effect towards your trait of interest. And with traditional genomic selection, we assume that these effects are linear in nature. So they have a linear relation. Each marker has a linear relationship to your trait of interest. And also that these genetic effects or markers themselves are additive in nature, so they can be kind of added together with some beta coefficients. But when we start applying traditional genomic selection on high demand or real genomic data, it starts to get messy. The biggest problem being high dimensionality of our genomic data, right? Where we almost always have huge number of markers, tens of thousands of markers, but with very few lines, like typical line size maybe like 200, 500, 600. So how do you apply statistical methods, whether it is traditional or machine learning, in the context of high dimensionality? And as plant breeding programs and breeding programs in general are getting more complex and more sophisticated, we're also collecting a lot of diverse types of data. So we start collecting other type of omics data. It could be transcriptomics, proteomics, etc., which have valuable information. There is weather data from the field experiments, soil data, and image data also from field experiments. So some of these data are very high dimensional in nature, like image data, can be quite complex to model with. But all of these individual data sources have valuable information that can help improve your prediction ability, and at the end of the day, help you in picking better lines or selecting better lines. And another common challenge, of course, is the complex genotype by environment interactions. So when we're modeling, we're also thinking about how do we include gene by environment interactions when you have multi-location, multi-trait data. So the opportunity that we have here with modern genomic selection is that we have all this richer data, and we now have access to more flexible models through machine learning that can potentially help drive better selection decisions. So where can flexible machine learning help? We'll talk about why I keep saying the word flexible in the next slide, but where machine learning can help is when you have these multiple sources of data, right? Whether it's weather, image, omics. When you have these multi-type data, which are also high dimensional in nature, machine learning can really help extract the right information from it. And when you also have larger data sets, it leads to nonlinear relationships between the markers and the traits of interest, or the G by E itself might contain some nonlinear signals. So and machine learning can generally help extract the best information from in these situations. But what I do want to emphasize is that machine learning methods are just one other toolkit in your wide array of genomic selection methods. Right? You have your linear methods, you have additive models, which also perform really well depending on the circumstance, depending on the data that you have. And so I want to emphasize that it may not always help. So, like, just because machine learning is like the newer, cooler thing, it doesn't mean it's the best model choice for your data. So, if the true relationship between your features, or essentially your traits and markers, is actually additive, if the true relationship is additive, machine learning actually might perform worse than linear models, which have this underlying assumption of additivity. And if you have really noisy phenotypes as well, like machine learning can sometimes have limited accuracy gains over additive structures. So, in terms of thinking about model choice from this end of like the simple linear models to the most complex, like neural network type of models, like we should aim to move along this line towards more complex models only if it has meaningful prediction improvement, right? If you have two models that one very simple, one very complex, and both have the same prediction accuracy, then simpler is better because it's just more explainable. We can understand the relationships in a more human readable manner. Let me take a pause here and see if there's any questions. I see a comment that some Amina is not seeing slides. Can I confirm that everyone else is able to see the slides?
I can see your slides, Vamsi.
That's your slide. Yes, sir.
Okay. Uh, Thank you. I mean, maybe you want to refresh Zoom. Maybe that'll help. Yeah. Okay. Essentially, like machine learning is where learning a prediction rule, we're essentially teaching computers to learn from data kind of by themselves. Like traditional programming or traditional modeling, we are very instructive in like these step-by-step rules of how to learn patterns within the data. But as we move towards machine learning, like the algorithms help teach the computer to learn without these step by step rules, right? And these rules are not something that we write hand by hand or in code. So what we try and do is provide the computer or provide the ML algorithm several examples. So, like in our case of genomic prediction, like we provide several lines with both the genomic information as well as the phenotypic trait that we have observed on the field. So we're providing the computer both like this informative data set along with the outcome. And if you give it several such lines, uh, and then use the right ML model, like the ML algorithm kind of learns the patterns that exist within the data. Yeah. So machine learning models also offer different levels of flexibility depending on the choice of model that we have, and each method itself comes with different assumptions. So one of the other key things I want you to take away is that uh, linear models have several assumptions that they rely on, right? But machine learning methods also have their own different assumptions. So it's not that machine learning methods have no assumptions and hence are easier to apply. So even like while applying machine learning methods, it's important to recognize the underlying assumptions and make sure that the data that we're using does actually respect those assumptions that we're making. And another key thing to take away about ML is machine learning provides greater flexibility in terms of those relationships that we are modeling, but it comes at the cost of interpretation. The nice thing with linear models is that once you've modeled the data in this linear structure, you have a direct linear relationship between your one specific marker and your phenotypic trait. Right? So it's easy for us as humans to understand that, oh, if the marker goes from 0 to 1 in this position, it leads to X% increase in the phenotypic trait. But with machine learning methods, because they're more complex structures underneath, we lose some of that interpretability. But again, the point of using machine learnings is prediction. So all we're trying to do is improve our predictive ability. And sometimes that leads to loss of like interpretability. Okay, so throughout this talk, I'll kind of use just a sample example. So this is based on a wheat data set. We will not like actually solve or apply these methods onto this data set, but it just helps with the conversation. So let's assume that the data set that we have is 600 lines with that are genotyped, and so we have 25,000 marker as the marker data set. The uh, data itself, like the phenotypic data, was collected in 4 target environments. So we have some like different environments. And we also have, from those field trials, we also have the weather and soil data. And so then our job now through this talk is to predict the yield for new lines. Right? So we're for the sake of simplicity, I'm assuming that we're not trying to predict the yield of lines in new environments, but just the same 4 environments that we already collected data on. And in terms of the genomic selection, we want to be able to advance the top 10% lines. Okay, starting with linear models and then seeing how we make the jump towards machine learning methods. So the most basic form of a linear model is that it predicts a response Y with the help of several predictors, right? Like these X1, X2, all the way to XP are predictors. In the case of our example data set, these X's would be the marker data, the weather data, or the soil data. And we're trying to predict yield, which we are representing by Y. So I hope most of you joined Alex Lipka's talks earlier in this lecture series. He did wonderful introduction to linear models and how linear additive structures can be used in genomic selection. So if you haven't had a chance to join those talks, the talks are uploaded on YouTube. So please go and look through. He's explained Bayesian approaches, lasso, and how to deal with the most common problem that we have of high dimensionality. So I'm building on that foundation, kind of assuming that you have seen some of it, but in case something is not clear, just let me know and I can clarify certain points. So the nice thing with the linear form is that we have this additive linear structure. But one of the disadvantages which we have because of high dimensionality is that if we try to apply ordinary least squares, it can be unstable because of this problem of P, like number of markers being greater than number of lines. And because we have this huge set of marker data, a lot of markers are also correlated. And so that can create some redundant predictors. So the most simple form of the linear structure may not be super useful in terms of getting good predictive outcome, right? And the key thing here is we're trying to improve our predictive ability rather than interpretability. So if you notice this, what we have is y is equal to this linear structure. In terms of a basic machine learning method form, all we're doing is kind of abstracting this equation into y equal to fx, where f is some kind of function plus our error term epsilon. So for the linear structure, it also follows this form. It's just that this f of x is this linear beta 0 plus beta 1 all the way to beta p. But for machine learning methods, this f can take a wide range of shapes and forms, right? So that is what allows a lot of nonlinear structure that we're able to model into the machine learning. So it broadens the shapes of the function or the relationship assumption that we have. And each choice of f that we have comes with its own different assumption. Let me pause here and see if there's any questions. Okay. Nothing for me yet. Okay, so what is, like we said, we've addressed or we've pointed towards this p greater than n challenge. This is the most common genomic prediction challenge, which is that the number of markers that we have is much greater than the number of lines. And so in our wheat data example as well, you can clearly see this, right? You have this 25,000 markers, that's your p, which is much greater than the number of lines itself that you have. And the common ways that there are several different ways we can address this challenge and ensure that our models still are able to work in this complex setting. And so some common solutions are regularized linear models. So these are some examples you might have seen is lasso, ridge regression, elastic net, etc. Alex Lipka again gave a wonderful introduction to this. I will also spend a little time on this in the next few slides because it acts as this wonderful bridge between moving from truly linear structures into nonlinear models. And then on the other side, we have Bayesian models that can help use priors to constrain this effect and help deal with this p greater than n challenge. The other is not even a modeling solution, right? Like before modeling, we can try to reduce this dimensionality. So this P is our dimensionality issue, right? High dimensionality issue. So we can try to reduce the number of dimensions that we have through there are several different dimensionality reduction approaches. More than happy to talk about these in Q&A or if anyone has specific questions at this point. But it acts as a wonderful pre-processing step that then allows us to apply well-known methods on our data set without having to worry about this high dimensionality problem. And then the other common solution is to reach for machine learning, where we are able to apply various nonlinear approaches to solve the same problem. And for today, we'll focus on the machine learning and regularized methods. Okay, so going on to one of the key slides in today's discussion, which is the basic blocks of a machine learning workflow. Right, so we start with data collection. So this data collection can be genotyping the lines that you have, collecting phenotypic trait data. So this could be yield, height, fruit color, fruit weight, etc. It could be weather data, again, from the field trials, environmental data, other omics data, which again is through genotyping. And we also have modern high throughput phenotyping data, which could be image-based data as well. Once we have the data that we want to collect, the first step before we jump into any modeling at all is pre-processing. So it helps clean up the data that we have. Sometimes we have missing data. So how do you handle missing data if the data that's missing is the trait itself? How do you deal with missing data if you have missing marker information for certain lines? So there's different ways to handle the missing data. And then in terms of helping with the modeling, something that helps a lot of different machine learning methods is normalizing and scaling the data. So what this does is brings different types of data into this common structure. Right? Like a simple example I can give is if you think of marker data, it's typically 1, 0 or maybe -1, 0, 1. But if you think of weather data, it's very granular, right? Like you can have temperature, which is in like 20 degrees Celsius, 40 degrees Celsius. You can have rainfall that is measured in millimeters. Maybe that's 50 millimeters in a dry area. That's 300 millimeters in a more rain-filled area. So you have all these different data types that have very different looking values. And so normalizing and scaling helps bring everything into a common structure, typically, let's say between 0 and 1 or 0 and 100. That helps the models not get confused by the different data types. So it's a very important step towards modeling success. So like if you want predictive ability of your machine learning method or even linear methods to work well, I think spending time on handling the missing data, normalizing and scaling helps a lot. The next is the evaluation strategy. So like I said, like it helps a lot to define what you're trying to measure and define what the performance metrics that you're trying to evaluate your machine learning methods against are. So you want to decide this beforehand and have this kind of evaluation strategy in place. As part of that, we also do something called data splitting, where we take the data that we have, we use some of it for training the model, some of it for validating the model, and then some of it to actually test the performance of the model. And so we want to have these three independent data sets to help evaluate our methods or machine learning models in a fair way, where if you have a new line or if you have a new environment, you want the performance of your model to be good, right? You don't want it to be good just on previously seen data. That's no point, because we already know the outcomes of previously seen data. And so splitting the data into train, validation, test helps a lot. Uh, in place of this train validation set kind of three split, you can also do cross validation, where you split the data into several parts. Again, Alex Lipka covered cross validation quite deeply, so I will not jump more into this. Please go back to his slides and have a look in case you're not clear what it is. And once you have all of this, then we jump into model training and tuning. This is where we use the training data, the validation data to fit the models, to tune the models, to improve their performance. And then the last step is prediction, where we then take this tuned models and apply it on our test data set to look at the prediction accuracy, to compare the models with different performance metrics, and finally select the lines. So if you look through this process, like as a data scientist or as a machine learning practitioner, I would say like in my day-to-day work or in the course of a single project, we spend a lot more time in the first three steps than in step 4 and 5. Like once you spend time being careful and cognizant of the first three steps, being really meticulous about it, model fitting actually takes the least amount of time, even though that's the part that is uh, looks fun and looks interesting to do. That's actually like the smaller part of your workflow. Okay, before we jump into this, let me pause and see if there's any questions. Okay. If there's no questions, we'll jump into the essentially section 3, which is evaluation strategy. Also having a look at the time, we're at 7:30. So, okay. So the goal of modeling is model accuracy, right? But training accuracy is not the goal. We want good performance on the test dataset, not on the training dataset. So most typically, mean squared error is used to measure prediction accuracy. I know like this looks like a complex formula, but don't even worry about it. Like all I'll say is y is the yield that you saw, for example, and f hat is the yield that you predicted. So what you want is that your prediction is very close to the actual outcome, right? So if these two are very close to each other, y and f hat, then this goes closer to zero and closer to zero. And then mean squared error, which is MSE, goes close to zero. Right? So a model that has really good prediction accuracy has an MSE close to zero. Right. So we use this to measure prediction accuracy often, but we have these two types of errors, right? We have the training data error, which is the performance of the model on training set, and test error, which is the performance on new data or that held out data set. If you do your modeling and you see low training error, that's really good. But what we care about is test error, right? So if you see low training error but high test error, that's actually a bad thing. It means that there's a specific term called overfitting. So what you've done is you've taught the model too well on your existing training data set. So it's learned all the little intricacies, and that actually makes it not perform well on new data. So this is a bad thing, right? We don't want high test errors. So what we want to try and do with all of our modeling and tuning is get low training error and low test error. In terms of simple breaking this mean squared error down, mean squared error can be broken down into variance and bias and some kind of irreducible error. So this is sigma squared is the irreducible error. We can't do anything about it, so let's not worry about it. But with our modeling choice, we can try to work on variance and bias. Because mean squared error is just the sum of these, if you reduce variance, you can reduce mean squared error. If you reduce bias, you can reduce mean squared error. So there are different ways to reduce mean squared error. And so we look at how each of the machine learning methods kind of works on one of these. Right. So what is bias and variance, right? This chart, I love this chart, is one of the most useful charts to explain what I would say is a key statistical concept. But let's leave aside the chart for a second, just looking at what does bias and variance mean, right? Bias is essentially the error from approximating a complex system with a simple model. So let's say your actual data is very complex, right? Like there are very complex relationships within your data, but you use a simple linear model to fit that data. Then what you're creating is this bias error because you have this complex system, but you're just using a linear structure. And so that leads to a bias error. And variance is how this prediction, which is your f hat, how does your prediction change if you're training on a different data set? If your model is a good model, well suited for your data, changing the training data set should not change your predictions much, right? So if it is changing a lot, it just means there's a lot of variance in your model. It's also not a good thing. Right? So if you then focus on the chart on the right here, what we want is this top left. This is ideal, right? You have low bias and low variance. So all these dots are, let's say, different model performances across different training data sets, and they're all closely bunched together. This is perfect. This is our ideal scenario. Sometimes you can have high bias and low variance. So this happens when you use a linear model, but the actual system is complex. So you can see like ideal is like we want to be in the center red, but because of high bias, we have moved away from the center. But because there's low variance, it's still a tightly bunched set of dots, but just away from the center. And on the other side, if you have low bias and high variance, you can see all these dots are kind of around this red circle, but they're all spread apart because it's high variance. And the worst thing that you can have is this bottom right, where you have both high bias and high variance. So they're not around the center, they're also spread out. It's kind of the most useless model performance that you can have. For small genomic data sets, so when I say a small data set, I mean small number of lines, high variance is a major risk. So what you have here is a common risk that we have with small genomic data sets. So then our objective is try and find statistical models, machine learning methods that can help go from here towards this way, where we try and reduce the variance of that data that we have, or variance of the performance that we have. Any questions here? Okay. If not, again, like essentially like all of machine learning, all of statistics, statistical modeling choices comes down to this one chart. I know it looks like a complex chart. I'll walk through it. It's really not, right? On the x-axis, what we have is model complexity. So from left is like low complex model. So you can think of like linear model. And then on the right end is your most complex models. So it's like complex machine learning models. And on the right is on the vertical axis is your error. Right? So if you have a low complex model, like it's possible that you have high bias and low variance, right? This is what happens with linear models is typically you have high bias and low variance. As your model complexity increases, you start reducing the bias, but the variance starts going up slowly. But what we want is kind of play around this total error curve, where we try and find the optimal model complexity for our data set. So this looks different for each data set, right? Like the general curve holds, but where it is changes based on your data set. But what we want to do is try and find this low point where we have minimized the variance and minimized the bias that we can get out of the data that we have. All right. So in terms of evaluation metrics for genomic prediction itself, it depends on the question that you're asking. Right? If you specifically care about how accurate are my predictions from my ML models, the most useful metric is mean squared error, or what is called root mean squared error. Mean squared error is what we just saw in a couple of slides ago. If you don't care about exact prediction accuracy, but you care whether predictions generally track your observations, so that's the chart on the right, then correlation is a good enough metric. You don't need to worry too much about mean squared error because you only care about whether they track the same direction. If we care about whether your selection rankings are correct, then a rank correlation can help more than correlation. And lastly, if the research question or the modeling question that we have is, did we find the best lines? Then a top K overlap is good. So for the case of our wheat example, because we care about the top 10%, selecting the top 10% lines, Like we can use either correlation or the top 10% overlap. All right. Just given the time, I will not go too much into this, but you can look through the slides later. For specifically for genomic prediction, there are different types of cross-validation schemes that you can do. So cross-validation is CV, but there's different kinds like CV0, known lines in new environment, CV1, CV2, etc. For our example, because we cared about performance of new lines in the known target environments, what we would want to evaluate is using CV1, which is cross-validation to help evaluate the performance of new lines in known environments. Okay, to kind of summarize the evaluation contract or the evaluation strategy for our wheat example, what we have is our prediction target is new lines. And so we use CV1 as our cross-validation scheme. Because we care about selecting the top 10% lines, we'll use correlation and the top 10% overlap as our performance metrics. So finally, we are at the exciting modeling side of things. Let me pause here and see if there's any questions.
Idris,
Okay,
please.
I see yes, I see one question in chat, and then I will come to you, Idris. So Antidius asks, in the evaluation metrics, where do AUC, precision, sensitivity, etc., come in? It's a great question. These are all evaluation metrics that are very commonly used in machine learning, especially AUC, precision, and sensitivity. These three are more useful when your outcome, like the trait of interest, is categorical in nature. So what I mean by categorical is the outcome is like a 1-0, right? So resistant to drought or not, resistance to salinity or not. And the other is you can also have multiple, it can also be used for multi-category. So this can be something like fruit quality, right? Fruit quality has, let's say, 1, 2, 3, or 1, 2, 3, 4, 5. There's also fruit color, which is also on a 5 scale. So for these kind of outcome variables, you can use precision, sensitivity, specificity, etc. Okay, let me take question from Idris. Sure.
Yeah, thank you for the presentation up to this moment. I just want to request for a little bit of uh, shedding more light on the CV1 and 2 because uh, for example, you said CV1. What I know about CV1 is that if I have genotypes evaluated across say, maybe 4 or 5
Mm-hmm.
locations, then
Mm-hmm.
I get the data sets. What I normally do is I would just extract the blues across the locations, which becomes like the general blues, the
Mm-hmm.
general performance across the location. Then I use that as the phenotypic data for the genomic prediction. Now, when I run into CV2, in most cases, I use the CV1 for parental selection. For
Mm-hmm.
example, I want to go into population development and advancement. So I could use that to select the parents, combining that with
Yes.
diversity information, then alongside with my heterotic pattern that I have in the breeding program. Now, if I want to use CV2, in most cases, I use the CV2 for genomic prediction for hybrid performance, wherein when
Mm-hmm.
I evaluate stage 1 hybrids, I evaluate in say maybe 4 or 5 locations. I have 8 locations, but sometimes
Okay.
resources may not allow me to be able to evaluate them in the 8 locations. I just probably may
Sure.
evaluate
Yeah.
using sparse testing.
Mm-hmm.
But before I use sparse testing, I used to use I used to have them replicated in say maybe 4 environment, 5 environment, then
Uh,
use that to generate the environment-based blues, which I now factor into the model to extract the J by E information that I would now probably
mhm.
use to predict the performance in unknown environment. However, it normally comes out with a very low uh, uh, what do I say, correlation. I mean, in terms of prediction, when I do my cross validation, it's usually very low in terms of the prediction accuracy. So
Right.
I sought some advice from a quantitative geneticist, and he advised that I could, instead of just using the 4 locations, I could use sparse testing across the 8 locations and see if it's better improve. So it's actually what I'm currently working on. So I just want to know if I'm probably on the right path with what I'm doing currently and looking back at what you're trying to explain with respect to CV1, CV2, and CV0.
Yeah. Thank you so much for the question, Idris. And I think you summarized the use cases of CV1, CV2, and sparse testing really well. I think you are on the right track. We also do have a sparse testing expert on the call. Nelson is on the call as well, in case he wants to add anything. But I think in terms of the cross validations, you're on the right path.
Thank you.
Thank you. Kwame, if you'd like to ask a question, and then we have a question in the chat by Dora. Kwame?
All right. Thank you for that. I just wanted to check on the trade-off between the variance and the bias. I just wanted to ask if you have any examples of how you would choose the appropriate model and how you would use the 2 parameters to do so.
Yeah, that's again a great question. Typically, when we do modeling, what we actually have control or what we are able to see is only the total error or the mean squared error, right? It's challenging to quantify the bias, especially variance is still feasible. Tough to quantify the bias because we don't know the underlying truth, right? Bias is essentially how far from the truth are we, but we don't know the truth. But so what we do is work with the total variance, but where the trade-off between bias and variance comes into picture is, let's assume you have 2 models, right? Both have the exact same total error. One of them is a linear model. The other is, let's say, a boosting model. Right? We'll look at what boosting is in a second. If we have these 2 models, boosting is a more complex model and linear model is simple. If both of them have the same total error, we know that linear models have low variance. So you could choose a linear model because it is low variance, or you could choose boosting because it is low bias but slightly higher variance. So the exact choice depends on what is your application at the end of the day. But my recommendation is always choose the simpler model, right? So that's where the bias variance trade-off comes in. Does that make sense?
Yeah, thanks so much.
Perfect. Thank you, Kwame. And then for the question on Dora, a great question again. I should have clarified that, yes, all of this is essentially for supervised models only. In terms of machine learning models, there is the area of unsupervised machine learning, but we will not look at that for today. Our complete focus for today's talk is just supervised machine learning. Thank you for the question and the clarification. Okay, so let's dive into some introduction of the machine learning methods themselves. Okay, so first one, like I said, is we look at a little bit of regularization. This acts as this lovely bridge between linear and nonlinear machine learning models. It also deals directly with the high dimensionality problem. So the problem that we have typically is more markers than lines, right? And when we fit this into a linear regression equation, the same equation can have multiple solutions. Many solutions work equally well for that equation. But the problem is that some of these solutions have huge and unstable coefficient, so which means there's high variance, right? And which is pretty bad for prediction. And this is where regularization or penalization helps. What we have are these three models, ridge, lasso, and elastic net, which penalize or which reduce the coefficients in different ways to help improve the stability and reduce this variance. Right? So what ridge does is it shrinks the effects towards zero, but doesn't actually make any of the beta coefficients exactly zero. On the other hand, lasso is amazing because it puts some of the effects to exactly zero. So what this also acts like is this natural dimensionality reducer, also like acts as an auto selector for markers. And elastic net does a blend of both. Okay? And so it's able to directly handle this high dimensionality problem. And regularization is super useful when your data is primarily genotype only and you have a limited sample size. So like some of the other more complex methods are difficult to implement. And one of the other nice things about regularization methods is that you retain all of the interpretability that linear models had because you're still in this linear equation structure. I don't know if I have it in the next slide. Yeah. Since you're still in the linear equation structure, you retain interpretability, and that's super useful sometimes in terms of understanding the relationships. I won't go more into detail about regularization. Again, like I said, Alex Lipka has covered it. So please go and look at his YouTube if you haven't already attended his talk. Another really popular class of machine learning models is based on decision tree. A decision tree is very simple, actually. Like one of the nice things and one of the reasons it's so popular is how simple it is, right? What it is it's a data-driven set of rules that split your data into several homogeneous subregions. So it's very simple, right? Like taking this example here, let's say you want to learn about decision trees. If you want to learn about decision trees, you're in the right Zoom room. We will talk a little bit about decision trees. If you don't actually want to learn about decision trees, you don't have to be in this lecture at all, right? You can go out and look at some real trees. Essentially, like each split in this decision tree is just a simple yes or no. And we keep splitting up your data till we form this homogeneous groups. So in this case, the two homogeneous groups is one group who wants to learn about decision tree and one who don't really care about it. Within decision trees, there's two flavors. One is called classification tree. So what you see on the right is an example of a classification tree. So it's predicting a category, right? Yes, no. But you can also have regression trees where you predict a numeric value. So we use regression trees quite more commonly in genomic prediction applications because your outcome is a numeric value, typically yield or something numeric like that. One thing with the decision trees is that it splits, it selects features by split, but it doesn't really deal with high dimensionality well. So it's not a super useful model by itself. But decision tree acts like a great foundation towards some of the more complex models. This is a very popular example of using decision tree is where we have this data set of three different types of iris flowers. So iris setosa, versicolor, and virginica. And we have data on their petal width, petal length, etc. And so you can then use a decision tree to kind of split. So the first split decision based on data we see is if the petal width is less than 0.6, it has to be setosa. So we've kind of separated this group. And then within the rest of the data where width is greater than 0.6, if your width is less than 1.7, then we need to look further. But if it is greater than 1.7, it has to be virginica. So essentially, like, you can kind of work down this decision tree to form these different groups or identify these clear categories of these iris flowers. The problem with decision trees is that it can lead to overfitting. You remember overfitting, right? It's a common problem where we teach the model too much about the training data and then it performs badly on new data. And the reason it happens is it grows too many splits. So like this keeps splitting, and so learns the data too well. And so the way to manage overfitting is actually pruning, where we cut out the lowest branches and make the tree a little more general. There's also other methods to deal with overfitting, like deciding the tree depth, deciding the samples per leaf, etc. There's also ensemble methods, which we'll look into next. So in terms of decision tree, the nice thing is you saw it's very easy visual to explain. It captures non-linear relationships. That's very nice. But the problem is that it's overfitting and also has low predictive power on its own. So the solution to deal with this low predictive power is we can combine many different decision trees and together have this more complex model that does not overfit and also has high predictive power. So there's two ways to do it. One is called bagging, where you take your data and train multiple decision trees in parallel. So you have tree 1, tree 2, tree 3, and then you average the prediction from each to get better low variance solution or low variance prediction. The other approach is in series, right? It's called boosting, where you create one decision tree, and then from that decision tree, you look at the mistakes it made, and then create another decision tree to reduce the error of the first one, and then in series till you have good prediction. So bagging helps with reducing variance, whereas boosting helps reduce bias. So we'll not go too much into the depth of bagging. Bagging is just bootstrap aggregation. I'll let you look at this slide at a later time, just given time. But what I want you to understand is this key thing, right? Bagging is trees in parallel. Boosting is trees in series. Random forest, which some of you may have heard of or all of you have heard of, is a specific type of bagging. So it's one form of bagging method where we are training these trees in parallel. But the way it works better than bagging is by decorrelating. So at each split, instead of considering all of the markers, it does a random selection of some markers and then does the split on that. So that's what I'm trying to show here is like initially it splits along one marker, then the next time it splits along a different marker, and then we average the results. What this does is it separates or creates more independent trees, which leads to better prediction accuracy. And because we're also doing this random marker selection at each split, it also deals really nicely with high dimensionality. So random forest is, I think, one of like a foundational method that builds on this decision tree, but has really nice performance in machine learning applications across the board. So the nice things about it is that it doesn't overfit. It's actually like quite resistant to overfitting because of the way it is just built. It's also parallelizable because we're building these trees independently. It's really fast to train, especially compared to boosting and some of the other more complex methods. The training of the data does not take very long, and it requires minimal pre-processing. So like because it's able to handle different types of data together, you can just throw in like genomic data with weather data, with soil data, and the random forest figures out the patterns by itself. Of course, the con is because now we're combining this, merging all these different trees, you lose interpretation. Like it's quite challenging to interpret the relationships using a random forest. And also, like as your data size grows, the computational cost grows. And so like if you have a really large data set, random forest sometimes can be quite slow to fit. So boosting is the other approach to combining different multiple trees, which is where it happens in parallel, right? So like you take your initial data, do a model, you look at that model, and then like you look at the errors that it's creating, and then build another tree based on the errors. So each new tree focuses on correcting the errors of the previous tree, right? And then the final prediction is combined across multiple trees. Boosting doesn't automatically deal with high dimensionality, and so it requires further handling. So like you can force shallow trees. When I say shallow trees, it just means like less branches. You don't allow very deep tree. You can control like early stopping, subsampling. All of these help handle the high dimensionality, but it does have higher risk of overfitting compared to random forests. Yeah. So, I mean, we've kind of gone through what random forest and boosting is, but from a practical point of view, like you can consider both when you have sufficient number of lines, and if you have multiple types of data, so you have marker data with some environmental data or management feature data, then it works quite nicely. Like, and it's minimal processing to get the model running. The last one is neural network models. Neural network models are these flexible function builders. These are the more complex form of machine learning methods. And it's loosely inspired by our biological neuron. So you have these structures called neurons, and they interact with each other to create really deep understanding of the patterns within the data. So here you have actually a mathematical structure of the neural, what is called a neuron, which is a single unit. So you have all these inputs. So the inputs can be marker data, weather data, etc. So that's all the inputs here. You have some hidden layers. We'll look at hidden layers later. And then each neuron has an activation function, which is like this nonlinear function that helps create the flexibility. And then you have the output, which is your prediction. Neural networks are one of the more complex machine learning methods. So this is what a typical neural network, like a simple neural network, looks like, where we have these input signals, which are our input data. We have the output signal, which is our predictions. But in between, we have what are called these hidden layers. So input layer is where the data enters. And then we have, in this example, we have two hidden layers, which is where the data is processed and patterns are identified. And then we have the output layer, which is your prediction layer. And this, now you can see like the model can be made very complex, right? You can decide within a hidden layer how many neurons you want. More the neurons, more complex the relationship. You can choose how many layers you want. In this example, we have 2 layers. Sometimes you can have 8 layers, 16 layers, etc. You can choose these arrows. Do you want every signal going to every neuron? Do you want to drop these arrows at random? All of these make the network really complex, and sometimes very, very helpful in prediction. So how does the neural network actually learn, right? I'm really simplifying the steps here. I have some more details in the appendix, which when I share out the deck slides, you can have a look. But essentially, like what we have is this forward pass, which is like we are just going through the neural network to the prediction layer. At the prediction layer, we measure the error. So like we see like how good is our prediction. Once we decide how good our prediction is, there are actually these backward arrows that inform each of the neurons what mistakes they have made. Right? That's where you backpropagate the errors. Once you backpropagate the errors, you then assign new weights to these arrows, like what is the relationship from this input layer to this hidden neuron. You update the weights and then go through the network again, do the prediction, look at the errors, backpropagate the errors, update the weights. So it keeps going in these cycles of forward propagation, backward propagation, forward propagation, backward propagation, till we improve the performance till we cannot improve the performance anymore. And then there's neural network, because it can form such complex relationships, it's also most prone to overfitting. And so there's several ways we can reduce overfitting. There's something called decay, dropout, early stopping. Again, like I said, we're not going into the details of these methods. This is just to present like some different options that you have within machine learning that might be helpful for your next genomic prediction exercise. Okay. So in terms of why neural networks are useful is their really strong performance when the true data is nonlinear or unstructured. When we say unstructured, a good example is like image data, right? Image data is more unstructured than our typical tabular genomic data. And so neural networks perform much better there. The other pro is because neural networks are so immensely widely applied in different fields, not just genomics, like it's applied across high tech, finance, AI applications. There are many open source libraries that can help you implement neural networks very easily. So you have standard libraries in R, in Python, for every different flavor of neural network. Even within neural network, there are different types. And for almost every type you can think of, there will be an open source code base that you can use to get onto your modeling very quickly. In terms of where it doesn't work well or why it can be sometimes challenging is that because of all the complex nonlinear relationship, it's basically a black box. We have no true understanding of the exact relationship between a single input marker and your output rate. It's also computationally quite expensive to train. Often, neural networks are not possible to run on personal computers unless you have really good computer resources. More often, it is trained using like high performance computing infrastructure. There's also heavy hyperparameter tuning. So we didn't look into hyperparameter at all in this talk, but the an example of hyperparameters is number of layers is a hyperparameter. So we have to make a decision on how many layers we want. Number of neurons per layer is also another hyperparameter. So like there's a lot of decision choices that we need to make to improve the performance of the model. And the last thing is it needs a large amount of data. So if you have very few lines, 100 lines, 120 lines, like neural network probably is not going to get you good performance. Okay, so this slide kind of summarizes the different methods that we looked at today and where each of their opportunity is within genomic prediction. So for example, like random forests, really useful if you have marker plus environment data. Neural networks, useful if you have large genotypic data along with multi-type data. One thing I want to emphasize is there is no single best method. The best machine learning model depends on your data, specific data, specific crop, what is the goal of your prediction exercise. But these are all different tools you can add to your toolkit to hopefully help explore more modeling choices the next time you're doing modeling. So in terms of just a simple guide on what we spoke about, right? If you have data that's primarily genotypic data and you have high dimensionality, the simplest is start with a regularized model. So it can be lasso, it can be ridge regression. Start there, and that acts as a great baseline. If you have enough lines and you have some additional data, you can also compare the baseline model with some tree-based models. So it can be random forest boosting, etc. And if you have high throughput phenotypic data, or if you have image data, you have sequence data, then you can consider a neural network. Okay, so going back to our initial example of our wheat, right? For this example data, like because we have high dimensionality, I think using lasso is a great choice to start as our reference model. Because the data also had uh, weather data and some soil data, we can try out random forests and boosting because it can help with the interactions and nonlinear effects. For this example, like I would actually not do neural network because we have only 600 lines, which I mean seems like a large size for genomic data or like breeding data, but for neural network maybe is small, and we don't have any large omics input. And I will pause there and take questions. Thank you so much for your time.
Thank you, Vamsi. We do have a question in the chat by Antidius. Antidius, if you'd like to unmute and ask a question.
Okay, thank you for the nice presentation, Mr. Facilitator. I just have a simple one question. I've been dealing with antimicrobial resistance data with the intention of deploying an algorithm, and one of my supervisors was suggesting that to go for the random forest algorithm because he considers it to be more interpretable compared to the gradient boosted decision tree.
Right.
I just wanted to know if this is methodologically correct from what you have explained from the boosting and with the random forest perspective. Thank you.
Yeah, that's a really nice question, Antelius. Can I ask a little more, like what is the problem that you're trying to solve? In your chat, you said clinical data, so I just want to clarify what your application is.
Okay, so basically it is a predictive problem where our outcome is categorical, where an isolate is either resistant to a given antibiotic or susceptible to it.
Okay.
Yes.
I see. It's a nice question. I think like the primary advantage that random forest has than gradient boosted is one is that because random forest inherently is able to provide feature importance as part of the algorithm itself, it
Yes.
makes it more interpretable. And
Yes,
so
yes.
you are able to, even though the feature importance score, it's not really directly meaningful, right? But it is relatively meaningful. And so that can add a lot of context from a scientific perspective compared to the gradient boosted decision trees.
Okay.
And so it's a common use case even in my current work. Like our preference generally is to use random forest based solution whenever we're trying to understand the relationship more than just increase prediction. So if I'm working on a machine learning model where all I care about is accuracy, then I would actually choose boosting, because boosting, especially something like XGBoost, is like incredibly powerful, incredibly well performing
Yes.
across different fields. But
Yes.
the problem with XGBoost is like you don't have the interpretation that random forest provides. And so like if we care about interpretation, RF like random forest would be suitable.
Okay. Okay. Thank you so much.
Yeah, thank you for the question.
Great. Do we have any more questions for Dr. Vamsi? I've put in a set of links in the chat for the next set of lectures, so please do register for them. Okay, if you think of any questions, you are also welcome to ask them on Thursday's lecture as well.
Yes, yeah, look forward to seeing all of you in the Thursday's lecture. I'm quite excited. It's going to be the first time I actually talk about AI in my daily workflow. I'm super interested. Hope to see you all there. But thank you so much for joining today.
Great. So thank you, Dr. Vamsi, and have a good evening, everyone. See you on
Good
Thursday.
evening. See you all. Take care.